that. Picture of the week for module number 4. For a lot of places, this is a good description of their security. This module is basically a continuation from last week, talking about cryptography and ways that it is implemented and used in everyday life. So while cryptography is understood and as necessary to users, what happens with an important encrypted file if it falls into the wrong hands? If that person who worked on it falls ill and can't return to work, how do you unlock that file to get the data without jeopardizing everyone's security? Remember that misconfigured cryptography is a vulnerability attackers know and will exploit. The first line of defense is key strength, or the resiliency of keys to attack. Obviously, the first defense to that is being random. The more unpredictable the pattern, the stronger the key. The second defense is key length. Shorter keys are easier to break. And the third is the crypto period, just the length of time for which a key is in use. Limited time prevents exposure and chances the cryptanalysis will compromise a key. This is the same or equivalent as with passwords. If you have a very small password, it's going to be easy to break. If your password is not random enough, it will be easier to break. And if you use the same password in more than one places and you don't change it often, again, it'll be figured out. Secret algorithms are not recommended for use. It is best to use a well-known and vetted algorithm to ensure that it works as intended. The goal of cryptography is to prevent the key and message from being compromised. The formula can and should be improved. Here's an example of block cipher modes of operation. The two shown here are the electronic code book, ECB, and the cipher block chaining, CBC. Which one's better? ECB is the most basic approach. Plaintext is divided into blocks, and each block is encrypted separately. This can result in two identical plaintext blocks into two identical ciphertext blocks that attackers can use to perform cryptanalysis and decrypt the message. Obviously, ECB is not considered safe for use. And yet you'll find it out and about. Cipher block chaining, CBC, is a common cipher mode. After encryption has been done, the ciphertext blocks are fed back into the encryption process to encrypt the next block. CBC uses XOR, so we played with that last week, on a plaintext block against the previous ciphertext before being encrypted. You also have things like counter that requires both parties to access a counter synchronously, using a new value each time a ciphertext block is exchanged. And a GCM encrypts both plaintext and MAC to ensure the message was created by the sender and not tampered with during transmission. Modern operating systems have built-in services to handle cryptography, just like printing, network, USB, and more. For example, in Windows, it's called the Cryptographic Services. In Linux, it's called the Crypto API. In order to make cryptography stronger. We need to make adjustments to input values, starting with something called salt. It's a value that ensures the plaintext won't consistently result in the same digest. Salt is normally used in password-based systems, although hilariously, it is not used in Windows. So what salt will do is you have a password called password, and you put it into a username. In Linux, 3 users could have the same exact password, and the encrypted value on the other end will be different. Not so in Windows. There's a nonce, another input value, a number used once. It's a unique value that's within a scope, like a given period or for a session, so like based on time. And there's also an initialization vector. You'll typically see this as IV. A number used once, selected in a non-predictable way. Used a lot in things like Wi-Fi. So here's a sad example of Windows. I'm going to use an awesome tool called CyberChef that I highly suggest you get familiar with because it is awesome. So I'm going to take a user name's password called password because they're lazy, and it's typically what we see is users tend to go for easy passwords on their system. The way that Windows takes that and turns it into a hash value to use later is it encrypts it in UTF-16, and then it does it in MD4. So you see this value over here in the output? If you go on a Windows system and you change their password to be password, like it is in the input, all lowercase, when you use a tool like Mimikatz to extract the passwords and see what the hashes are for those passwords, you're going to find this exact line because this is how it works. So I kind of listed in the notes how you can download the tool and run it. You have to disable antivirus because antivirus will tend to stop this. But you could totally run this on Windows and then find that whatever password you type here and you set that password on a user account, you'll get the same exact output. It's pretty fun. So yeah, so log into a system. Here, let me go back to my slides. Create a Windows VM. Doesn't matter what it is. Don't forget to set your password. You could use a super secure password like this one. And there's my output. So I disable my antivirus by going to run as administrator. Of course, I want to run this. And here I disable the Windows Defender and restart the system using the instructions that I put in the lecture notes. Download Mimikatz. At this time, it was 2.2. I get the Mimikatz trunk.zip. Then I'll switch directories where I'm at, run the command to unzip it. then go into the folder that's now there. And then I'll run Mimikatz. Once it's running, I run those 2 commands in order to be able to grab those keys. There is the password. There's the exact match. Any questions? Did I go too fast? Did this just rock your world?
Very interesting, that's for sure.
Feel free to replicate on your own system or on a cloud system, but understand that that on Windows, it is ridiculously easy. So what somebody can do, honestly, is get a list of all possible passwords, run it through something as simple as CyberChef, and get the outputs for every possible password. And now they have a nice, accurate dictionary to use. And as you saw, I mean, look, this password is not at all something that you'd find like using the word password or let me in or 123. I mean, that password that Google gives you is definitely a secure one. It's random. Doesn't really match with anything. But yet, the way that Windows functions is it saves it in a way that's easy to figure out. So just have a nice fat dictionary of all these, and it doesn't matter what somebody types, it'll be easy to figure out. So if I need to run through that again, let me know. I can also do it afterwards. Otherwise, I'll continue with the slides.
Could you do Mimikatz one more time for me, Irvin? This is Dan.
So the Mimikatz portion is you'll need to go on the, here, don't go back. I have on the lecture notes, there is a link that will take you to the Mimikatz page on GitHub. You'll download the trunk.zip file. Or you could actually just right-click this and get the link for it. And then within PowerShell, you would change the directory to whatever username you're logged in as. You would invoke web request and then paste the entire link of where that zip file is with an output to mimi.zip. I just did mimi.zip just because I'm lazy. And then expand archive so that it will unzip what you downloaded and then go to that folder. Then you'll start, oops, that's in the way. Then you'll actually run the executable. But you can't do this until you do the other things first of like disabling antivirus. And then once you're in it, you'll run these 2 commands in order to see what's happening. And then number 2, grab all the passwords. And within the list that you'll get are the results. You'll see your username, the system, and you'll see the NTLM password. And you'll see that it'll match exactly to whatever you did with whatever password you inserted into Windows. So this cannot be done with Linux because Linux uses salts. So if 2 users input the same password on their accounts, they're going to get different hashes. And they don't use NTLM. This is a specifically Windows thing. They use Blowfish instead. So a account in Linux is far safer than an account in Windows. Continuing the road in digital certificates, which is another way to implement cryptography. Just like your government issued ID card proves who you are, a digital certificate is used to associate a user's identity to a public key that has been digitally signed by a trusted third party. A certificate can be seen as a container for a public key used to identify objects other than users, such as servers and applications. As with a physical ID card, certificates have a signature, a serial number, and an expiration date. Digital certificates have authorities. When a user wants a digital certificate, they must first generate their key pairs, the public and private. After this, they complete the request with information such as their name, address, email, and so on as part of the certificate signing request, or CSR. The request is signed by the user's public key and sent to an intermediate certificate authority who performs the function of a certificate authority, otherwise known as a root CA, who is responsible for digital certificates. These intermediate CAs can ask the user for authentication by email or documents or in person if required. Just like getting your license or ID from the DMV, there's a basically equivalent process to get a digital certificate. Of course, just like IDs, we have fake IDs. People make fake certificates. They're prime targets to be compromised. A compromised certificate authority would taint all the intermediate CAs that work with them and their certificates. One way to prevent this is to have the root CA offline and only brought up when renewing intermediate CAs.
So the CA is a human being that you interact with, or a piece of software?
It could be a piece of software. It could be a server who hosts the digital certificates. And that the root one is the one you don't want to have on all the time to prevent it from getting compromised. Because it's like DMV having master copies of everyone's IDs. You don't want those to get compromised and then people make fake ones of yourself and others, or whatever. So you want to protect that as much as possible. A certificate repository, as seen here in Windows, is a publicly accessible centralized directory of digital certificates. The certificate revocation list is for expired or compromised certificates that come through either the certificate revocation list that is sent online or the online certificate status protocol, or OSCP. Windows Server, for example, can call out to an online certificate status and find out, oh, these certs are renewed, these certs are expired, these have been compromised. There's a whole network for Windows Server to issue out or prevent certificates from being used any longer. OSCP is a real-time lookup certificate, real-time lookup, kind of like DNS, typically called the request response protocol. OSCP stapling is another way to get a response to a browser for every query as part of the TCP handshake. So you have a web browser who wants to connect. First, we're going to validate the certificate. It says, yes, here's the signed one. It goes back to the browser. Now the browser can use this approved and active certificate. So here's a chart that helped me make better sense of this. So yes, Equifax does have a root digital certificate, and then they can team up with others to be intermediates. And then you could have your own website that you can issue a digital certificate for, like using Let's Encrypt. And you'll have your 90-day cert that is backed up by all these, including the root digital certificate. Just like your ID card can be backed by the state government or the federal government. There's multiple layers behind every piece of valid identity. So certs can be chained together to establish trust between any and all certificates that are involved. So every certificate from the root all the way down, all of these will be chained together. So if one of these becomes compromised, the others can take over. That way, the end user site is still active, even if one of these three gets compromised or goes offline or has any problems. They're still validated, they're still good to go. We see digital certificates pretty often in web servers. They ensure the authenticity of the web server to the client, and they ensure the authenticity of the cryptographic connection to the web server. This allows HTTPS connections to be secure over the open internet. Web servers and clients use a key exchange to set up their communications, as shown here. The web browser starts the conversation, going to a site. The web server returns back to hello and says, these are the algorithms I support. The web browser will then create a cert or verify the cert and create the pre-master secret. That's exchanged back to the web server, confirmed. The master key and session keys are created. And now both the web browser and the web server can talk to each other using HTTPS in a secure fashion. Sites that use HTTPS are secured with a domain validation digital certificate or an extended validation certificate, which has enhanced verification processes. There are wildcard certificates that validate the main domain along with any and all subdomains, typically seen as something like star.class.com, for example. Subject alternate name certificates are used with unified communications like Microsoft Exchange and integrating with email, SMS, fax, etc. The subject alternative name allows different services to use the same certificate for validation. There are hardware and software certificates. For example, at the machine level, verifies the identity of a device in a network transaction. There are certificates for code signing used by software developers to sign a program proving it comes from a legitimate source and hasn't been altered. And also certificates for email. The formats that you tend to see the most come from the International Telecommunications Union, or ITU. They adhere to the X.509 standard. Now, as far as the Security Plus test, that's what you need to know. The ITU X.509 standard is the most used for digital certificates. Within this cert, there are three things you need to know. There is the Privacy Enhancement Mail, or PEM. It's designed to provide confidentiality and integrity to emails. There is the personal information exchange, or PFX, the preferred format for creating certificates to authenticate apps and websites. PFX is password protected as it has the key pair within it. And lastly is the PKCS number 12, one of 15 standards defined by RSA, based on the RSA public key algorithm. Like PFX, it has the key pair inside. So if you've ever worked with like Let's Encrypt, you will have seen those file formats. And Let's Encrypt is actually pretty easy to use, which is great. So you can protect your site with ease. So having these certs sounds great, but we need to build a way for people to access our site and verify the certificates on the fly. So in comes the public key infrastructure. This is used to manage the public keys and digital certificates. This includes hardware, software, people, policies, and procedures to create, store, distribute, and revoke those certs. The first one that I'm showing you here is the first trust model called the hierarchical one root certificate authority system, who signs all the certificates with a single key. This is not in any way ideal. If the root CA is compromised, all the certificates become worthless. Having one system to verify and sign certificates can also cause a backlog when you scale. This is the distributed model. We have multiple certificate authorities who will sign certificates. There is also redundancy built into the system should any one CA system be lost. The root CA can also delegate the workload to ensure a faster response, because we all know one thing that users hate is a slow computer. This is bridged. Similar to distributed, bridged has a facilitator CA that doesn't issue certificates, but acts as a hub between different trust models. So again, these are all different ways that we can implement multiple systems to handle a large amount of traffic coming to, for example, our web server, who want to connect to us and validate that we are who we say we are. Like, for example, Amazon will have a lot of these, a lot of certificate authorities that every time a phone or every time a browser goes to their site, they'll get authenticated and then pass, start their usual traffic to do business. But that first part of validating that will take time if we don't have an infrastructure built in to quickly respond and say, here, we do have a valid certificate. We are who we say we are. Let's connect and go from there. Certificate policy provides recommended baseline security requirements for the user and operation of a root, intermediate, CA, and other components. Certificate policies should cover the obligations of the certificate authority, the user obligations, confidentiality, operational requirements, and training. Certificate practice statements is a more technical document describing in detail how the CA uses and manages certificates, how end users register for a cert, how to issue certs, when to revoke, procedural controls, key pair generation and installation, and private key protection. The X.509 certificates have a place for their associated certificate policy. What I'm showing you here is the life cycle of a certificate. They're created and issued to a user. After some time, they will be suspended if there is no more action necessary. It'll get revoked after a certain amount of time, and then the revocation list will get updated, and then it'll be expired, and a new one will be issued. This is ideal. It is ideal for certificates to get expired and to create a new one, because you don't want someone to figure out the keys. You don't want anyone to understand how those certificates are being created and then generate their own illegitimate, but ones that will work. So it is best that a certificate be created and let expire and create a new one to take its place. A couple more terms with digital certificates. The key handling procedures. We can have an escrow where the public or the private keys are being managed by a third party. Private keys can be split in half, each encrypted and stored within the third party. So if a user combines and saves a copy, it will render this defense useless. There's expiration. An expiration date prevents keys from being used indefinitely in case they are copied without anyone's knowledge. For example, if an employee quits after a while, if their key doesn't expire, they could keep using it to siphon out data. Again, there is renewal, but it is discouraged. You don't want to continue using certificates and keys for longer than you should. Revocation. Revoked keys cannot be reinstated. It's an immediate effect on the key. What I have a picture of here is a recovery. A user's private key is encrypted and divided into a specific number of parts. The parts are distributed to other users with overlap so that multiple individuals have the same part. For example, 3 parts can be distributed to 6 people, with 2 having the same part. This is the N group of a M of N control. If a key needs to be recovered, the M group can piece together the key. This way, no one person has the key, but you have to grab a couple of people together in order to make it happen. And the last 2 in key handling procedures are suspension. This is the temporary pause on a key, and destruction, removing all the public and private keys along with the user's identification information in the certificate authority.
So how long does a key, or how long should a key exist before you go through this process and issue a new one?
So the last year, there was a moratorium that placed certificates age up to 2 years. That was the maximum. So that would be the longest you could have a certificate and key pairs, 2 years. I kind of like the 90 days that Let's Encrypt does. I think that's long enough that you'll use it for a while, but short enough that you won't be able to, the risk of it getting compromised is low because it'll go out in 90 days. So this is a small list of protocols that use cryptography to secure communications. It's not in any way exhaustive, but we use these to communicate securely. So like SSL, which has been around since '94, TLS, Secure Shell using port 22, HTTPS using HTTP traffic over TLS, SMIME for emails, SRTP for things like VoIP, and IPsec. Any questions on this little lecture?